So welcome to the Emergent Constraints and Tipping Points workshop that's been arranged by Paul Ritchie, Mark Williamson and me at Exeter. It's really supported by an ERC ECHLS project that we're involved in, and also Crescendo Horizon 2020, 4C Horizon 2020 project, and the ClimathNet network as well. So we've basically been thinking for a while, actually before the COVID pandemic, of having a workshop on these two topics for reasons that Mark will explain in a minute as introduction. But for those of you who don't know me, I'm Peter Cox, based at Exeter, and been thinking about emerging constraints for a while now, and the links to tipping points more recently, which we hope will come out of the meeting. I just wanted to very briefly go through the way the meeting will operate. This is purely because, you know, these days with online working, you sort of need to have there's a certain formality to the way you do things that's required. I think we're all used to this now, but just to refresh us on this. So the first thing to note is that we have deliberately got different timings for the meetings on Monday and Tuesday, when we'll run till, from 4 till 7 GMT, and this is partly to accommodate people over the Atlantic who've got different time zones but otherwise have to get up really early. And then on Wednesday and Thursday, we're going to go for 2 till 5 instead. So just be aware of that, slightly different timings. As you will see from the schedule that Paul sent round, the meeting's made up of 20-minute keynote talks and 10-minute offered contributions. And we were very excited to get so many of the latter in such a short amount of time. So many thanks for those. I think the programme looks really exciting. We are, however, going to try and run this quite tight because we want to get a lot in without having people online for hours and hours. So we ask speakers to keep to their allotted time so that we've got plenty of time for discussion. The chairperson of each session, which will be rotating between Mark, Paul and me, will basically let you know as a speaker when you've got 2 minutes left. So that'll be 8 minutes after in a 10-minute talk and 18 minutes in a keynote. And then when the time is up. And throughout, what we've found with online meetings is that if we can use the chat box whenever it occurs to us, speakers will generally not be looking at this because it's distracting, but we can have a kind of buzz generated from that. And then the chairperson will draw on the questions posted in the chat box after each talk. So you can either post things that we ask speakers, or if you'd like to speak yourself, just type an exclamation mark in the line of the chat box. And we know that anything after exclamation mark, or if there's nothing that you would like to speak about something directly. And that would be great because it means you hear more than the voices of us and the speakers. We would like, as I've said, to record this talk meeting. And there are plenty of people that have said to us, short notice, I can't make it, I'd love to be there. So where speakers haven't told us that they don't want their talks posted, please let us know. It won't be done immediately. We won't be doing it without your say so. We're not planning to post the discussions because they're often less well thought out, and we want to have a very free form discussion. But where speakers are happy with it, we'd love to be able to post the talks on a website at a slightly later date. So with that, we'll go on to the actual meeting. So today, day one, session one, is on emergent constraints. So today and tomorrow on emergent constraints, and then Wednesday and Thursday on tipping points. And we're going to begin with an introduction to the scientific aims of the workshop from Mark Williamson. So Mark, are you all set to share?
Yeah, should be. I think you're going to have to stop sharing.
Yeah, okay.
How's that? Can you see that?
Yeah, I can see that. Just need to go full screen.
Okay, hi everybody. So I'm Mark Williamson. Peter's asked me to give overall context to the two topics in the workshop and how they're linked, at least in our brains, when we jump between the two fields. So the emergent constraint stuff is today and tomorrow between 4 and 7. And just to tell you briefly what emergent constraints are, it's a method to constrain a real world unknown using model ensembles and observations. So it's one of a bunch of possible methods. So the idea is, you look at this schematic, you have some observable in the real world on your x-axis, something you can measure now, and you want to link this to something you want to know in the future on the y-axis. In this case, this system sensitivity. So you don't know this in the real world, you can't find it out in the real world, but you have models, and that's what these red dots are. They're each individual climate models. What you want to do is find a relationship between this thing you can observe now and this thing in the future for your models. This relationship we call an emergent relationship. So it's a low-dimensional relationship in model ensembles between something you can make in the real world and something you want to know for the real world. So the good thing about this, if you can find such a relation, is that now you have this relation, as long as it's, you can define some functional form, the model's spread across a range of values. You can measure this thing in the real world and then infer in the real world what your unknown sensitivity is. And that's what you call the emergent constraint. You've constrained the real world through an emergent relationship. So to give you an example of this, probably best known and the first emergent constraint was this one introduced by Hall and Q in 2006 for the snow albedo feedback. So they're observable in the real world now was the strength of the snow albedo feedback due to the seasonal cycle. And the thing they wanted to know was the strength of the snow albedo feedback on the y-axis due to climate change. And not surprisingly, that they're linked. They did this originally in this CMIP3 model ensemble, but since then it's been verified in later generations, CMIP5 and CMIP6. And you can see the real world is this grey bar, and the implied change in the snow albedo, the implied strength of the snow albedo feedback due to climate change is approximately the same as the snow albedo feedback due to the seasonal cycle. But there's been a bunch more emergent constraints for different parts of the Earth system found now. And during this workshop, we'll have talks on climate sensitivity. So these are talks by Manuel Schluntz, Nick Watkins, Aurelian Reed, Fem Kanisa, Tim Palmer, Cassia Tukarska, and Richard Wood. There's ones on the carbon cycle, talks by Rebecca Varney, Ryan Padron, and Jens Terham. Emergent constraints on clouds, Nicholas Lutzko, and on the cryosphere, that's Chad Thackeray. I should also say there's a whole bunch of reviews that do a much better processing all this information, putting it in context. One's by Hall, Ryan, and one by ourselves that's been submitted. So how might low-dimensional climate relationships appear in ensembles of climate models, given that climate models in the real world have very high dimensional parameter spaces, and their responses are generally functions of all these parameters? Well, the null hypothesis is they just occur by chance. They're not indicative of a deeper predictive mechanistic relationship. And that's a real danger in small ensembles to work with, although they're getting larger. So there are dangers of data mining and p-hacking, there are statistical errors and assumptions. But also they might be indicative of approximate deeper mechanistic relationships when certain responses are dominated for a few degrees of freedom. For example, this is an effective dimension reduction, those huge numbers of parameter space dimensions reduce effectively to a few. This can happen when a particular response becomes sensitive or when the range of values of one process in a model ensemble is large relative to the other processes controlling that response, or the other parameters are relatively weakly coupled to that response. So they're very simple relationships, and they're a very powerful way of gaining understanding on climate models, but because they're simple, there's a variety of ways they can go wrong. So this is something people are investigating. So chance relationships can be guarded against by using a predictive theoretical basis to be independently falsified. You can have overconfidence in the statistics because they're low-dimensional relationships. You can guard against this by taking into account all sorts of uncertainty. You have missing processes and feedbacks in the latest models that aren't there in the real world. That would skew your emergent relationship. You can have compensating errors in models. Errors in observations or observations that are not directly comparable to model outputs. And there are talks about these topics roughly by Peter Colwell, Ben Sanson, James Annette. I'd just like to say emergent constraints can be a very powerful tool to reduce uncertainty and promote understanding of the important processes in a variety of climate projections, provided one's aware of the possible pitfalls. So they have had occasionally a bad rep because there have been data mining expeditions. But awareness and understanding these pitfalls should lead to EC research becoming more rigorous and more useful. The second topic of this workshop on Wednesday and Thursday, this is different times between 2 and 5 GMT, is tipping points. And these are abrupt changes in state caused by small changes in the forcing. Just to illustrate a particular tipping point, this is the AMOC, so the Atlantic Meridional Overturning Circulation, in a freshwater hosing experiment for a particular climate model. And as the freshwater hosing is turned on, you get this really abrupt shift from overturning to not overturning. So it's this blue to red transition. It's very, very abrupt, even though the change in the forcing is quite smooth and regular. So there are various different types of tipping that are studied. All require more than one stable state. Probably the best known example is this tipping from a local bifurcation. So you have two possible stable states, but gradually as some parameters changed or some forcing has changed slowly and smoothly, this initial stable state loses stability and then abruptly shifts to a new state, finds a new stable state, and this is manifested as this big jump. This is known as local bifurcation tipping. You can also have noise-induced tipping. I should say the tipping from a local bifurcation, a good example is possibly the AMOC. The noise-induced tipping example is possibly a dansk event. So here, the stability of the two or more stable states doesn't change, but the random forcing can occasionally be large enough to flip one state over this potential hill and into the other one. So there's no change in stability, it's purely noise driven, and there's very limited in these events as well, just because they are probabilistic. There's a third one as well, this rate-induced tipping. Again, there's no real change in the potential landscape here. It's just the control space is shifted so quickly that the state can't recover or relax back into that original stable state. It finds itself over in the other well. And a particular example of rate-induced tipping, this is known as, could be the compost bomb. And there are talks in the workshop by Joe Clark and Owen O'Sullivan on this. And there are other talks on types of tipping, broadly speaking, by Hassan Al-Qayoun, Chris Hassan, Paul Ritchie, Ulrika Feudal, and Peter Ditlevson. I should add, if I've got roughly the topic of your talk wrong, I apologise. That's roughly classified it that way. So there are possible climate tipping points. These were identified by Lenton et al. I say possible because they're not confirmed. For example, there was the AMOC, the cryosphere tipping points. So you can ask questions like, what can tip? Under what circumstances can they tip? What's the probability? What are the impacts of a tip should it happen? Are there any early warnings of a tip? And can one tipping point tip another tipping point, and so on in a cascade? So there are talks on particular tipping points during this workshop by Frank Kwasniok and Johannes Lohmann on the AMOC, the cryosphere, Ricardo Winkelmann, the Amazon by Nico Wunderling, and social tipping points by Martin Scheffer and Tim Lenton. So I'll just try and link tipping points now to emergent constraints through this idea of early warning signals. In this case, it's early warning signals of a particular tipping point, this local bifurcation tipping. So what happens there is this, as one of those states loses stability, you can treat the perturbations linearly, essentially. So they're noisy perturbations, and the dynamics is approximately linear. In that case, you can calculate the system, some statistics of the system as a function of this sensitivity lambda. And changes of these statistics can be used as your early warning of tipping. So just go back to our fold bifurcation. The system's gradually losing stability as it comes down here. It's being perturbed by noisy random forcing. And just before the tipping event, you can calculate the statistics of these noisy perturbations, in this case, the variance and the autocorrelation. And what you look for is essentially an increase in these statistics. As these statistics increase, provided the forcing remains constant, then you can tell that the system's losing stability. And there's a talk by Nicholas Spurs on early warning of tipping later in the conference. So one link between tipping points and emergent constraint research that we use, we came in via the tipping point method actually. So to detect an early warning of tipping, you want to detect a change in systems sensitivity from an observable. And a useful theoretical basis for an emergent relationship serves to diagnose a constant system sensitivity from an observable. So we can use the same mathematical technique for both, i.e. the statistics of the perturbation away from the steady state are functions of the system sensitivity. And this is what we did with a simple energy balance model. Using, again, the variance and the autocorrelation, you can diagnose a system sensitivity, and we use that basically as the foundation for an emergent relationship we look for in an ensemble of climate models. But that's one link we exploited in our own research, but there are probably many more. So we'd be very interested to hear about them. But thank you for attending and enjoy the workshop.